Hello everyone, welcome back. Here's VanAmsen. Today we have an exciting coding challenge to tackle, finding the longest common subsequence between two strings. So this is a classical problem that's often asked in technical interview, and we will be solving it in Go. So before we dive into the code, let's quickly go over what a subsequence is. So subsequence is a sequence of characters that appear in the same order as in original string, but not necessarily consecutively. So for example, in our example, so let's dive into example right away. So given text 1, it's A, B, C, D, E, and text 2, so it will be A, ace. So the longest common subsequence is ace. So output should be 3. And as you can see, if we delete B and also delete D, we have ace. So it's subsequence. So now when we understand the example and what the task asks us about, and before we dive into coding, let's first discuss the logic behind solving this problem. So understanding the core idea will make the coding part much more intuitive. So the problem of finding longest common subsequence, or LCS, is a classic in computer science, and it's often solved using dynamic programming. Why dynamic programming? Well, this problem has both optimal substructure and overlapping subproblem. So two main ingredients for dynamic programming solution. So the optimal substructure is the solution to the problem can be constructed from optimal solution of its subproblems. So for example, if we have text 1 to I, so let's write it down. Text 1 is 1 to I, and text 2 is 1 to j, and if it is known that there is LCF of between those two texts, we can derive it further to text 1 to 1 I plus 1, and text 2 I, so 1 j plus 1. So it's really important. And also the overlapping substructure. So when we try to solve this problem recursively, we solve the same subproblem multiple times. And dynamic programming allows us to store the result of these subproblems in a table, so that when we have same subproblem, we don't to compute it one more time. So we will use a 2D array, often called a DP. So let's call it DP I j, and it will contain the length of LCS between text 1 to I. So this will contain text I and up to text j. So LCS between those two texts. And we will initialize the first row and first column of the DP table to 0, because a string with 0 length has LCS of length 0 for any string. And then we will populate the rest of the table, moving from the top left corner to the bottom right corner. And if the character at text ij, so we have ij, are the same, we have a common element for LCS, and we will update our DP with DP of I plus 1, j plus 1, and also add here plus 1. So one more character. So here is minus dp minus 1 and dp j minus 1. So it's previous state. And if there are different, then either text at I or text at j, so then we don't have LCS for both. So we will then, so it's otherwise, so it's one case, let's say, or else, so it will be second alternative case. So it will be our max between previous states of dp I minus 1. Here is also minus, and here minus, typo. I minus 1 j or dp I j minus 1. So it's really common transition function, and you will see it a lot in dp programmer. And also we store our result in dp of m n after all calculation. So now that's we understand the logic. Let's translate it into coding. So first thing first, we need some helper function. So it will be function max a and b int, return int. So if a greater than b, return a and return b otherwise. Okay, so as simple as this. And now let's dive into main part, so implementing our dp. So mn will be len text1, len text2, and initialize a 2D dp array. So dp will be make array of int m plus 1, and for I range dp I make int n plus 1 and fill the dp array. So now the filling part, and for I1 I less than m increment, and for j1 j less than n increment as well. And if text I equal 1, text 2 j1 dp ij dp I j plus 1. So our transition that we talked previously, and else it will be dp ij will be max between dp I minus 1 and j or I j minus 1. So, and finally we return dp at mn. So implementation is much easier than writing. This is implementation. So as you can see, it's quite straightforward and follow the logic. And we initialize 2D array called dp with dimension m plus 1 times n plus 1. So let's run it to verify it's working. So yeah, all works well. So I'm submitting it. So hopefully it will run. Yeah, it's running. So wow, it took 10 milliseconds. So previously it was just 4 milliseconds. So we can even rerun sometimes if you rerun. Yeah. So second run, you see 4 milliseconds beating 93%, and it's quite optimal. And in dynamic programming, we loop through each cell of dp array and fill it based on the character text1 and text2. And if character matches the match, so we add 1 to the value of the top left diagonal cell, and if they don't match, we take the maximum value between the cell above and the cell to the left. So it's also like really classic. So the beauty of solution is that it uses dynamic programming to optimize the time complexity to OM times n. So it's not only efficient, but also elegant. So we could solve this using recursion, but that would be much slower, even if we use memorization. So it's quite optimal solution, but not only one solution, because every problem could be tackled with different algorithmic approach. So for those of you interested in other programming languages rather than Go, I will include the Python, C++, Rust implementation in the description below. And alright, that wrap up today's live coding session. If you found this video helpful, don't forget to hit the like button, share it with your friends, and subscribe for more awesome coding content, challenges, tutorials, machine learning, and much more. And until next time, happy coding, stay motivated, and see you next time.